We're going to start looking at a very interesting aspect of quantum mechanics and modern physics, which is exploring how devices work, how metals conduct electricity, how semiconductors work, what are insulators, what are metals, and this is of course something that has direct relevance to our daily lives as well. But quantum mechanics and modern physics give us unique perspective on the mechanism of conduction and how electrons behave inside metals. So our general notion of conduction is the following. We have a metal, say copper, aluminum, gold, silver, and inside the metal we have positive ions, which are the nucleus and the core electrons, and they are fixed in space. So I'm representing these positive ions by these yellow circles with a positive sign in them. So this is a rigid structure or frame of positive ions, and these positive ions comprise the nuclei as well as the core electrons. And the valence electrons, they are free from the ions, they do not belong to any atom, and they are inside the metal, and there is a sea of electrons. For example, an individual electron that is moving around the ions, it moves in straight lines in 3 dimensions, it collides with an ion, changes its position, moves in a new direction, collides again, and this process continues. So there is a swarm of electrons, a soup of electrons around fixed positive ions, and this is called the sea of electrons. And this is how conduction takes place. You apply an electric field, and the electrons, being charged particles, they experience a force. The force is given by minus E, capital E, and the electrons accelerate, and their acceleration is simply given by minus E over m E. So under the action of this applied field, the electrons accelerate opposite to the direction of the electric field because they are negatively charged particles, and when they accelerate, their velocity increases, their speed increases. So if the electrons have an initial speed vi, if an electron has an initial speed vi, after time t it acquires a speed vi minus em e over into t. This is the speed after time t. Now the electron is continuously being accelerated, its speed is increasing until it finally strikes an ion. It collides with an ion, and as a result of the collision its velocity changes because it starts moving off in another direction, and it starts off with a new initial velocity. But in between collisions the velocity is continuously increasing, right? Because there is a constant electric field. Time is continuous, of course. Time is not quantized, time is not discrete. Time is a continuous variable, so with time the velocity keeps on increasing until a collision happens and the electron changes its course. फिर किसी और तरफ चल पड़ता है इलेक्ट्रॉन, फिर उसकी स्पीड इंक्रीज होती है, then it hits a collision, then the process starts again and again, over and over again. So the velocity keeps on increasing continuously, and the energy as a result, which is the kinetic energy, is half m v squared. Now v is a function of time. Since the speed is increasing continuously, the energy keeps on increasing continuously, and there is nothing quantum about it. So this is our classical picture of conduction inside a metal. ठीक है, copper wire ले, you take a jumper wire, you put a battery around it, a current starts flowing through the wire, and this is the classical picture that comes to our mind, and this was the picture that existed in the 19th century. This model is called the Drude model. Drude was the name of the scientist. Drude's model. There's nothing quantum about it, but there are certain problems with this model. Before I tell you what the problems are, let me invoke the quantum picture straight away. Let me tell you how quantum mechanics comes to rescue us and what alternative paradigm the quantum picture presents. Because quantum mechanics is a revolutionary idea. It always comes up with counterintuitive explanations of a well-known classical phenomenon. Conduction is well known. Conduction was well known from Faraday's time, electrical conduction. We knew what conductors are. Benjamin Franklin had discovered electricity. But when quantum mechanics came to the fore, when quantum mechanics threw light on many beautiful aspects and phenomena of nature, things changed. And what is the quantum picture of conduction? Now these electrons that are inside the metal, they are just like electrons trapped in a three-dimensional well. So this metal is three-dimensional and you have a free electron, or you have an electron inside the well. And we know that the energy levels for such an electron, they become quantized. Okay? If you remember our discussion of electrons trapped inside the well, the energies are quantized because of the boundary conditions. Remember, localization leads to quantization. Now the electron is localized. It has to remain within the boundaries of, within the surface of the metal. It's inside the metal. You're not freeing the electron from the metal. No thermionic emission or photoelectric effect is taking place. Electrons remain inside the metal. They are bound inside the metal. So it's just like an electron trapped inside a three-dimensional well. Now for such a well, we know that the energies are quantized. So we have a large number of energy levels inside the well. And for the time being, suppose that there is no degeneracy. That is, the metal is not a cube, rather it's a parallelepiped with all three sides unequal. And when the three sides are unequal, there is no degeneracy because there is no symmetry. So all of these are non-degenerate levels. Now these levels, there's an energy level and then there's a spacing, there's a gap between the next energy level. There's a gap, then there's a gap, there's a gap, there's a gap, there's a gap. And this axis is the energy axis. Now look at the beauty of quantum mechanics. Now there's an energy quantization, energy levels which the electrons can occupy inside this metal, they are quantized and they happen in discrete steps. Electron can exist only in an energy level. It cannot exist in a gap because its energy is quantized and discrete. So this level is the lowest energy level, then the first excited level. And these are, you can imagine these to be empty levels, and you have a large number of electrons and you want to put electrons into these levels one by one. So if you have a large number of electrons, you take one electron and put it into the lower level. Now you have another electron, the second electron. You put it into the lower level. You have a third electron. Suppose you are at 0 Kelvin. There is no temperature. Everything wants to be in the ground state. You put all the electrons into the lower level. But this is not allowed. Why is it not allowed? Naively or classically, we would expect all the electrons to be in the lower level at 0 kelvins. Okay? But even at 0 kelvins, when you put one electron inside this energy level, it has a certain spin. It has a certain value of ms. We know that electrons in a 3 dimensions, they have 3 quantum numbers. We know that. It's a 3-dimensional system. We have 3 quantum numbers, N, L and ML. But we also know that there is a 4th quantum number, which is the spin. And the projection of the spin is ms. So these 3 quantum numbers come from the Schrödinger picture, and this 4th quantum number comes from Dirac's equation. It's the spin of the electron. And this spin can take up 2 values, plus half and minus half. Okay, only 2 possibilities because the electron is a spin half particle. So instead of 3 quantum numbers that define an electron, we really need to work with 4 quantum numbers. The fourth quantum number has nothing to do with these quantum numbers. They define the spatial part of the wave function, which depends on r, theta and phi. This is the spin part. So the wave function psi has to be defined by these four quantum numbers. Okay? So the wave function really has a radial part which depends on n and l. It has a polar part which depends on L and ML, an azimuthal part which depends upon ML, and we've learned that inside the wave function, if you want to write the total wave function, you need a spin part as well. Let's denote the spin part by some chi. Chi is some other function, wave function. I just give it a name chi, and chi is dependent on ms, and ms can take two values, plus half or minus half. Plus half could be denoted by an arrow pointing upwards, and minus half could be denoted by an arrow pointing downwards. These are just labels, these are just conventions. So the total quantum state is to be defined by four quantum numbers. This set of quantum numbers defines the total quantum state of the electron. Now if you have one electron inside this energy level, there is a wave function corresponding to this energy level, okay, and to this electron. Now if you want to put another electron into the same energy level, this part of the wave function remains unchanged because it's the same energy. Okay? But the spin quantum number can either be upwards. This is one possibility. The other possibility is that you have the two electrons. In one case the spin quantum number is plus half, and in the other case the spin quantum number is minus half. These are two possibilities, possibility A, possibility B. Since this possibility versus this possibility, they are in the same energy level, they share the same spatial part of the wave function. देखो wave function क्या है? Wave function n, l, ml, ms depends on r, theta, phi and spin, right? The wave function depends upon these four variables. So you have a spatial part, let's call it alpha, which depends upon r, theta and phi, and it depends upon n, l and ml, and chi, which depends only on ms. It does not depend upon a space variable. For these two electrons, they are in the same energy, so they have the same value of this function alpha, because they are located at the same, they have the same dependence on r, theta and phi. They are identical, they have identical spatial parts of the wave function, but the spin quantum numbers can either be identical or they can be different. Now there is an important relationship or an important principle in quantum mechanics that is called Pauli's exclusion principle, and we will derive this principle later, but first I would like to show its applications. The Pauli's exclusion principle simply states that no two fermions can have the same set of all four quantum numbers. Let me write this down for you. So this is a strong version of the Pauli's exclusion principle. So you have two electrons in the same energy level, electron A and electron B. So don't take these spheres too literally, but just for purposes of illustration, this is electron A, electron B. They are in the same energy level. They have the same energy, therefore they will have identical wave functions as far as the spatial part is concerned. Okay? Which means this will have an N, L and ML, and this electron will have the same set of N, L and ML. Therefore, according to the Pauli's exclusion principle, the fourth quantum number must be different. So if one of these electrons has ms plus half, the other electron must have an ms of minus half. This is the only possible way of collecting these electrons into the same state, into the same energy level. They will have the common spatial part of the wave function but different spin parts. Therefore, you would represent one electron with an arrow pointing in the upward direction representing the spin or the magnetic moment, and for the other electron having its spin in the downward direction with an ms equals minus half. And an electron is a fermion because it's a spin half particle. So fermions obey this version of the Pauli exclusion principle. Bosons don't obey this. So photons, which are spin 1 particles, they are bosons. They can all be put in the same state. They can have, all of them can have the same set of quantum number. That's what happens in a laser. All of the photons are acting in unison. They are acting together. They have the same quantum state, but not for electrons or fermions. Okay? So in a level, you can have at the most 2 electrons with the same energy, occupying the same energy level. They have identical values of the spatial part of the wave function, but they must have opposite spins. And you can only put 2 electrons inside the level. You cannot put in a third. Because if you put in a third, its spin will either be parallel to one of them, and that's not allowed. So these possibilities don't exist. The only possibility is that you put one electron into the lower level, then the second electron goes into the same energy level. It has the same energy but opposite spin. Now if the Pauli exclusion principle were not active, you put a large number of electrons, you can put in a third electron, a fourth electron, fifth electron, you can put in all the n electrons in the lower energy state. This is what classically is predicted, because that will lower the energy. All the electrons are in the ground state. Agreed? But that's not possible quantum mechanically. That's not possible by virtue of Wolfgang Pauli, who postulated the Pauli's exclusion principle. That's not possible. So now you have a third electron. All of these levels are available to you. ठीक है? आप कहीं भी जा सकते हैं, लेकिन आप lowest energy में जाना चाहेंगे. But Pauli's exclusion principle forbids you from going into the lowest energy state because it's already filled. So you find the next vacant state, the next vacant level, and you put the third electron in here. A third electron in here with any spin you like, and then you put in a fourth electron into the same energy level with an opposite spin. So you keep on filling these levels. So 2 electrons in each level until you exhaust all the electrons. Okay? You have a large number of electrons, you exhaust all the electrons and keep on filling these levels up to a maximum level. Okay? You can't go beyond it because you don't have more electrons. If you had more electrons, you can keep on filling. When you've exhausted your electrons, see, the metal has a fixed density, it has a fixed number of valence electrons. So there's not an infinite supply of electrons in a metal. There's a finite supply of electrons. So because the metal as a whole has to be neutral as well. So you keep on filling these levels until you reach an upper level. And this upper level at 0 Kelvin is called the Fermi level. In honor of the Italian physicist Enrico Fermi. The highest field level at 0 Kelvin is called the Fermi level. Alright, now look at the power of Pauli exclusion principle. देखो, electrons behave like human beings. That is, they repel one another. Two electrons, even these two electrons, they are not in the same state. They have the same energy, they have the same values for 3 quantum numbers, but the 4th quantum number is different. So electrons tend to repel one another, and this repulsion is not of electrostatic origin. देखो, ये repulsion जो है, why don't these two electrons allow a third electron to occupy the same energy? It's because of a quantum mechanical principle which is called the Pauli exclusion principle. It has nothing to do with electrostatic repulsion. So this Pauli exclusion principle is a kind of repulsion between the electrons, but this repulsion is not of the electrostatic origin. It's a purely quantum mechanical origin, and we'll derive the Pauli exclusion principle, or we'll motivate it later, but this is a consequence. So these electrons एक दूसरे के साथ मिलना गवारा नहीं करते, बोसॉन्स गवारा कर लेते हैं, ठीक है, सारे इकट्ठे मिलके काम करते हैं, ठीक है, एक चलता है, सारे फिर साथ उसके इकट्ठे होकर चलना शुरू करते हैं, फिर दूसरा तीसरा सारे इकट्ठे फिर चलना शुरू करते हैं, ठीक है, लोग साथ मिलते गए और कारवां बनता गया, वो बोसॉन्स की बात है. लेकिन ये नहीं, फर्मियंस नहीं ऐसा करते, इसलिए लेजर्स photons हैं वो सारे इकट्ठे चलते हैं. They are all in phase, they have the same quantum state, superconductivity, all the Cooper pairs are in the same state, you have superfluidity, you have all these exotic effects. So there's a difference between bosons and fermions, and the energy of the system is automatically increased. देखो, classically you would expect all the electrons to be in the lower state. So if this lowest energy is E1 and you have n electrons, the total energy of the system would be E1 times n. But now you have a large number of electrons that are above the ground state, so total energy goes up. ठीक है? So in metals the electrons are moving at very high speeds. In metals the electrons have very high energies because of the Pauli exclusion principle. And the Pauli exclusion principle is at the heart of two very diverse effects, and we will study both of these effects. One, we will study metals, semiconductors, conductors. Pauli exclusion principle determines how these bands are made and how these metals conduct electricity. And on the other hand, the Pauli exclusion principle describes black holes, it describes neutron stars, white dwarfs, red giants. So it's describing the macrocosm, the very large objects which are beyond our imagination. They're so large, and they are also describing the tiny ICs and the tiny semiconductor devices. So this is the real range of applicability of quantum mechanics. And the beauty of quantum mechanics is that with one principle, with the Pauli exclusion principle, we can study both of these at the same time. We can look at the macrocosm and the microcosm at the same time. हम ये दोनों चीजें देखेंगे अगले कुछ lectures में. But now we're going to look at metals. Now I would like to invoke the concept of bands. What are bands? Now suppose you have a 3-dimensional well and an electron is trapped inside the 3-dimensional well. ठीक है? So what is the energy of the electron? It depends upon 3 quantum numbers, nx, ny, nz, and this is given by pi square, h bar square, 2m l squared, nx squared plus ny squared plus nz squared. So this is the energy of an electron trapped inside a three-dimensional cubic well. ये याद है ना formula? अच्छा. Now suppose we have a metal, a three-dimensional metal. It's a cube of a certain length L. Suppose this is 1 centimeters. And suppose the energy of the electron is 1 electron volts. ठीक है? Let's suppose that this energy of the electron is 1 electron volts. A typical energy, 1 electron volt is the typical energy of an electron inside a metal. ठीक है? देखो ionization energies 13.6 electron volt, 10 electron volt, 5 electron volt इसी रेंज में होती है ना एटम्स की. तो द एटम इज फ्रीड फ्रॉम द आयोनिक कोर एंड इट्स नाउ इनसाइड द सी ऑफ इलेक्ट्रॉन. सो दिस इज द टिपिकल एनर्जी ऑफ एन इलेक्ट्रॉन. It has to be smaller than the work function, because then the work function is 2 electron volt, 3 electron volt. So the energy has to be smaller than the work function, otherwise the electron will be ejected from the surface of the metal. So this is a good order of magnitude estimate of the energy of an electron. So with this value of the energy, can you find what this factor should be? You can perform a calculation. You know what the energy is, you know what the length is, and you perform this calculation. Nx squared plus ny squared plus nz squared is simply E 2ml squared over pi squared h bar squared. And this turns out to be, I've done the calculation, about 8.8 into 10 raised to power 13. It's a very extremely large number. ठीक है? So it's an extremely large number. This means that this electron will exist in an energy level which is 10 raised to power 13 steps above the ground level. Which means that I have to draw 10 raised to power 13 levels. I keep on drawing, right? And then I would remember Ghalib's शेर. कब से हूँ क्या बताऊँ जहाने खराब में, शबहाए हिजर को भी रखूँगा हिसाब में. It's so long, it's so long, it's such a long process. I have to draw all of these levels. 10 is about 13 levels on the blackboard. And an electron with energy 1 electron volt. I will keep on counting these number of levels, and I would get roughly 8.8 into 10 raised to power 13 levels. I will draw them, and this electron will sit on this number of, on this index of levels, right? So there will be large number of levels. Keep on. So there's a large number of levels. Now what is the spacing between these levels? I would like to determine what the spacing of these levels is. Are these levels closely spaced or they further apart? Remember, this energy is about 1 electron volts. ठीक है जी? Okay, sorry. ठीक है. About 10 is per 7. ठीक है? Sure, thank you. All right. Now suppose I am in an energy level Nx, Ny, Nz. I am in this I have this quantum state, this set of quantum numbers. I move to the next level. When I move to the next level, suppose I advance Nx by 1 and keep the others constant, I will move to the next level. Agreed? So I have to find the difference delta E between two consecutive levels, and that difference will simply be of the order of pi square h bar squared 2ml squared nx plus 1 whole squared plus ny squared plus nz squared minus nx squared plus ny squared plus nz squared. Correct? This is the energy spacing between two consecutive levels. Pi squared h bar squared 2ml squared, the nx squares will cancel out. I will have 2nx plus 1, right? So since nx is so large, I can ignore this one. Pi squared h bar squared ml squared nx. So this is the energy separation between two consecutive levels. Now what is nx? I know the value of nx squared plus ny squared plus nz squared. I can assume that nx, ny and nz, all three of them are the same. I can assume that. So 3nx squared is almost the same, is about 10 raised to the power 13. Okay? Which means nx squared is about 10 raised to the power 13 divided by 3, which means nx is about, I would say, 10 raised to the power 7. I take the under root. I'm doing order of magnitude calculations. So this energy separation is pi squared h bar squared m l squared into 10 raised to the power 7. So can you perform this? Can you find out this energy separation delta E? It's about 10 raised to the power minus 8. Sorry. Alright, it's not 10 to the minus 8. You can find out the value of the energy separation. Now what I really need is this energy separation delta E divided by the total energy, which means how large is this energy and how much is this energy spacing. Okay? So this delta E will be equal to pi square h bar squared ml squared. What is delta E? Nx. And what is E? E is simply pi square h bar squared ml squared nx squared plus ny squared plus nz squared. Correct?
So the value of delta E that you found was between this level and the one afterwards, right? It isn't for general, right? It's not for every two consecutive levels.
It's for every two consecutive levels.
So how would that?
Because nx, ny and nz, the next consecutive level is found by advancing or just one of the quantum numbers.
But the value of nx that you used, that was for the last.
That I'm using for the top of the band or the topmost level. ठीक है, ये समझ आया? चलो यार, ठीक है. We're talking about orders of magnitude here. Okay, so ml square 2nx divided by, I call this 3nx squared. Two over 3 is almost 1. On the order of nx and nx square, we're talking about orders of magnitude here. 10 was 17, 10 was 13. So this is 1 over nx. And what is 1 over nx? Nx is 10 to the power 7. So what is 1 over nx? 10 raised to power minus 7. So what does this mean? This means I have a large number of energy levels, an extremely large number of them. And if this energy is 1 electron volts, I have 10 million levels in between. I have 10 raised to power 7 levels in between. So within an energy of 1 electron volt, I have 10 million levels. I have to draw these 10 million levels. Okay? So the levels are indeed quantized, but the levels are placed so close together. They're placed so close together on the energy scales we're talking that these levels appear continuous. So these levels, the resolution of these levels or the spacing between these levels is so small because we have to draw a large number of them. These levels are spaced so close together that this set of levels appears continuous. Okay? So you can replace this set of energy levels by a continuum, okay, which is called a band. So if you put a magnifying glass on the band, you will actually see these fine energy levels. You will be able to look at the quantum picture. But on a coarse scale, these energy levels are placed so close together that they appear to form a continuous spectrum of energies, and those continuous spectrum of energies is called a band. This is just like reading at a newspaper print. I mentioned the quantization aspect very early on. You have individual lettering, but when you look at the newspaper from a distance, the individual lettering is not obvious, it's not conspicuous. You see a smudge of ink on white paper. But if you go close enough, if you go at the quantum level, if you can have a resolution at this energy scale, you will be able to see the fine levels. So this is what is meant by a band. And a band has electrons in it because there is a distribution of electrons from the lowest level to a filled level. So this band can be filled up to a certain level. This is the ground energy. It's called the bottom of the band, and this highest filled level is called the, क्या कहते हैं इसको? Fermi level. So you can have a band that is filled with electrons. So this is the filled part of the band and this is the vacant part of the band. So you can have a vacant part, an unfilled part in the band, and you can have a filled part. मैं अभी बताऊंगा बाद में. ठीक है, यहां तक बात समझ आ गई? कुछ क्वेश्चंस थे एक आध. जी आप पूछो. डेल्टा ई देखो, डेल्टा ई डिपेंड कर रहा है एन एक्स और एन वाई और एन जी की वैल्यू पर. ठीक है, सेम 3 डायमेंशनल वेल में सेम तो नहीं रहता, उसमें द एनर्जी स्पेसिंग इज डिफरेंट, सो इट्स नॉट कांस्टेंट थ्रू आउट द बैंड. अब मैं बताता हूँ आप तो देखो ये बैंड है पूरा यहाँ तक, येलो पार्ट तक, लेकिन यहाँ तक फिल हुआ है 0 केल्विन पर. दिस इज कॉल्ड द फर्मी लेवल. The band can have vacant levels as well. I will explain that in a minute. Now what happens on the scale of conduction? You apply an electric field. Now this band, I draw the picture of the band again. Okay, because there are certain things I would like to highlight. The band ends here. but the electrons are filled up to this level. So this is the Fermi level. I call it EF. Okay, and I'm always at 0 kelvins. So I have electrons in this band, and if I look closely enough, there will be 2 electrons per level, and there will be a large number of levels. Okay, and there will be an electron 1 or 2 at the Fermi level. Suppose there are 2 electrons at the Fermi level, and there are electrons all the way down. But now I am drawing this not as levels but as a band, because now I am looking at this at the scale at which the band structure is evident, not the finer details. But the finer details do exist. If I look closely enough, the finer details exist. Remember that. Now what happens when I apply an electric field? When I apply an electric field, a force acts on the electron. It accelerates. It gains energy. The Drude model. So we know that when an electric field is applied to a metal, the electron must gain energy. Alright, so look at this electron. If it gains energy, can it move to the upper state? No, it can't, because the upper state is already filled. An electron that is in the middle of the band cannot gain this energy, because the upper level is filled. देखो, electrons continuously gain energy, so it gains energy, but this electron cannot gain that energy because it cannot move to a higher level, because the level is already occupied. ठीक है? This electron cannot move to a higher level because it's already occupied. The Pauli exclusion principle is determining which electrons can gain energy. Only the electrons that are at the top of the band, that are able to see empty levels above them in the band. So I'm drawing these empty levels by orange lines. These are empty levels, vacant levels. Empty levels. So only electrons that are at the Fermi level or close to the Fermi level, they have available vacant levels to which they can make a transition. And they will make a transition in jumps, because an electron can gain an energy delta E and move to the next level. This delta E is fixed, it's quantized, it's a small energy, but it can only make a jerky movement. It can only increase its energy in jerks because of quantization. So only the electrons that are at the Fermi level can contribute to conduction, and they will gain energy and they will move to a higher level. Remember, we are talking about 0 kelvins. Okay? So you keep on giving energy. This electron has now this level has now 1 electron. An electron from the lower energy level can now take up the position of this vacancy that has been created by the electron. So it can start moving. So conduction, the onset of conduction starts at or near the Fermi level, and the electron must have vacant levels above it inside the band to be able to conduct. जी डायरेक्ट नहीं, क्योंकि उसकी एनर्जी ने तो कंटिन्यूसली वेरी होना है ना, उसकी वेलोसिटी कंटिन्यूसली वेरी हो रही है बिकॉज इट्स एक्सेलरेटिंग. So it cannot get an energy of 10 electrons in one go. It has to start gaining energy slowly and slowly. Therefore conduction happens at the Fermi level. Jumps में होगी, लेकिन in quantum mechanics stop thinking of the electron in motion. ठीक है, वो उस तरह एक्सेलरेट नहीं हो रहा, उसका एक वेव फंक्शन है, वो मैं अभी बताऊंगा. ये सारी बातें आहिस्ता आहिस्ता आएंगी आपके सामने. अब देखें, मैं आपको 3 डायग्राम्स बनाता हूं, बैंड डायग्राम्स. ठीक है, उनमें फर्क देखते हैं. Let's look at picture number 1. This is the energy axis. This is picture number 1, picture number 2, picture number 3. Let's look at picture number 1 first. Suppose this is the ground state energy Eg, E0, and this is the Fermi level. The Fermi level, the energy band goes from E0 to the Fermi level, and then the next band, then there is an energy gap, a large energy gap, Eg. This is the gap. There are no levels inside this gap. Why are these gaps formed? I will tell you later, but there is a gap, and the next band starts after a gap. Okay? The next band starts after a gap. Suppose, now this is the Fermi level, it is at the top of a band. It's at the top of a band. Then there is a gap, and the next band is after the gap. So since this is the Fermi level, electrons exist inside the band all the way up to the Fermi level. But this is a large gap. Now if you give electric field to such a material, the electrons that are at the Fermi level do not have enough energy, or they do not have adjacent vacant levels to which they can make a transition, because there are no levels inside the gap. The Fermi level is already at the top of the band. There are no vacant levels above the Fermi level. You have to cross a very large barrier in order to move into this band, because this band does have vacant levels. This band does have vacant levels. These are vacant levels here, and these are filled levels. So an electron does not have enough energy to cross this gap. This is like a barrier. So such a material, if you apply an electric field, it cannot conduct, because the Fermi level is at the top of the band, and after the band there is a gap. If such a material were to conduct ever, what would you need to do? You need to apply such a strong field, such a strong electric field, that this electron at the Fermi level can gain enough energy to cross this gap. That is, you must give it an energy greater than E times Eg. You must apply a force that is greater than this much, right? Such a material is called an insulator. So in an insulator, there is a band, and the band is completely filled, and then there is a gap. After the gap there is a vacant band, but the gap is large. So the Fermi level is at the top of the band. This band is given a special name. It's called the valence band. Valence band. And this band, which is empty for an insulator, is called the conduction band. And this is totally empty. And this is the band diagram for an insulator, such as diamond, wood, air. All of these are insulators, and the band gap is so large, it's of the order of 5 electron volt, 6 electron volt. For diamond it's 6 electron volt. So this is the band diagram for an insulator. Air, you come across the word dielectric breakdown of air. क्या होती है dielectric breakdown? What is dielectric breakdown of air? Anyone at the back? Spark होता है जब air conducts electricity, बिजली चमकती है, हवा में चमकती है ना बिजली. So conduction of electricity. But air is an insulator. But the voltages are so large. They are of the order of kilo mega volts. The voltages are so large. The clouds acquire so much charge that the voltages between clouds and the voltage between the cloud and the ground is so large that the air no longer remains a conductor, an insulator. Which means enough energy is given to the electrons so that they can cross this gap. Zara khamoshi se. They can cross this gap. A capacitor that you use in your electrical engineering laboratory, it's rated for a certain voltage. 5 volt ka capacitor, 20 volt ka capacitor. When you look at power system, 240 volt ka capacitor. Because if you give more than this much voltage, the dielectric material in the capacitor will break down and it will no longer remain a capacitor, it will become a conductor. So when you supply enough energy to overcome this band gap, this energy gap in an insulator, the insulator starts conducting. But this is the band diagram for an insulator. For a conductor, we have a valence band and a conduction band. And the valence band is completely filled. Khamoshi se sune please. And the conduction band is partially filled. Now the conduction band is partially filled, which means that there are neighboring empty levels inside the conduction band, and an electron at the Fermi level, at the Fermi energy, can easily make a transition to a neighboring vacant level. So you apply an electric field, an electron at the Fermi energy or close to the Fermi energy can gain energy. It can gain energy and move to a vacant level inside the band, because there are vacant levels inside the same band. These electrons do not have to cross any gap. So this is the picture for a conductor. अच्छा, और बताओ आपने कि रिपीट, पहले रिपीट कर देता हूँ, ठीक है, लेकिन पहले रिपीट कर दूं, ठीक है, क्योंकि कुछ कह रहे हैं रिपीट कर. अच्छा देखो, ये जो बैंड है, दिस इज अ कंप्लीटली फिल्ड बैंड. अगर ये यही बैंड होता तो इंसुलेटर होता सिर्फ हमारे पास. नाउ देयर इज अ गैप and then there is another band which is called the conduction band. Now this band is partially filled, it's not completely filled. So this is the Fermi level to which the electrons are populated. The electrons exist up to the Fermi level, but right above the Fermi level there is a vacant level at a spacing delta E. There are other vacant Now what happens when you bring these circuits close together? That is, you bring this RLC circuit closer to this circuit so that there is mutual inductance between these inductors. That is, your new circuit becomes this is some load. Your new circuit becomes something like this. Now, what are the resonant frequencies of this system? Will they be omega 1 and omega 2? No. The resonant frequencies will change. They will become omega 3 and omega 4. And this circuit will now have two resonant frequencies. Some omega 3 and omega 4. Okay? Now let's take this discussion further and look at bands. And why do we get these gaps? Suppose you're talking about lithium. Now lithium has an atomic number 3, has 3 electrons, an electronic configuration of 1s2, 2s1. So you have two lithium atoms that are very far apart. This lithium atom will have a certain energy level. It will have an energy at 1s and an energy at 2s. So this lithium atom will have a 1s level and a 2s level. And the 1s level is completely filled with 2 electrons pointing in the opposite direction and an electron with energy of the 2s orbital. And this is one lithium atom, and you have a lithium atom that is far away, very far away, so that the two atoms don't talk to one another. So you don't have a solid, you have a gas of lithium atoms. Two atoms that are very far away, they are independent. So you have a 1s and a 2s. Now what happens when you make a solid? When you make a solid, the density must increase, that is, the atoms must come close together. देखो वहाँ पे हमारे पास दो RLC circuits थे, they were further apart, they have distinct frequencies, but when you get closer together, the frequencies change. Now we have two atoms which are really oscillators. You can take this analogy here. Now bring this atom close to this atom. What happens is that this energy level starts splitting. This energy level starts splitting. That is, instead of one level, you have a large number of atoms, large number of electrons, a large number of energies, and a large number of frequencies start appearing. In fact, just consider two atoms. Just consider two atoms for the time being. Sorry. So, this energy level will split up into two, and this energy level will split up into two. Likewise, this energy level will split up into two in an identical fashion, and this energy level will split up into two in an identical fashion. So now you started off with two levels in two atoms. When you bring those two atoms close together, you have four levels. 1, 2, 3 and 4. You have four levels. Okay, यहाँ पे in one circuit you have two frequencies. You started off with one frequency per circuit. When you bring the two circuits close together, you have two frequencies in the same circuit. Now you're bringing two atoms close together. So bringing two atoms close together, each one of them started with two energy levels. Now you have a system, a two-level system, a two-atom system, and a solid which has two atoms in which there are four levels. Now, if in a solid is not made up of two atoms, a solid is made up of a large number of atoms, millions, billions, trillions, zillions of atoms, large number of atoms. So, in such a with such a large number of atoms, you do not get 4 or 6 or 8 levels, you get a large number of levels. And those levels are so close together that you form bands. And then there is always the probability that there exists a gap between this band and this band. So with a large number of atoms, you would get a large number of energy splittings, a large number of component levels. So these two levels are now split up into a large number of levels. You get a band. The 2s level is now split up into a large number of bands. अभी मैं बताऊंगा, पहले मुझे खत्म करना है, ठीक है? तो देखो, अब हमारे पास अगर n atoms हैं, if you have n atoms, we get n levels, and these levels now form bands, and there is a natural splitting between the 1s and the 2s level. There is a natural splitting between the two Bohr energies. There is energy gap between 1s and 2s. आपको पता है वो gap कितना है? So that gap, it's very possible that that gap appears within these bands as well. Let me make another more illustrative diagram. I'm short of blackboard now, but I can try it. I'll finish and then answer questions. So this is the 1s level, the 2s level, the 1s level in another atom, the 2s level in another atom. Now you bring a large number of atoms close together. In the Bohr's model, there is a gap between these levels. We all know that. This is minus 13.6 electron volt. This is minus 3 point something electron volt. There is an 8 electron volts gap between these levels. Now when you bring the atoms close together, these levels fan out. These levels spread out. Each atom will contribute 2 levels, but there is a large number of atoms. So they will all contribute, each one of them will contribute 2 levels. At the end you will get a large sequence of levels which have different frequencies. Just in complete analogy with bringing a large number of circuits together, you will get a large number of resonant frequencies, a large number of energies at which the circuit resonates. So because of bringing the atoms close together, these levels are now split up. And you get a large number of them. And the spacing between these levels is so small that these levels appear continuous. If you have only a few atoms, then you cannot form bands. You get these discrete levels. But if you have a large number of atoms and you bring them close together, the level spacing is so small that this appears to be one band, this appears to be another band. Now if you look at the system of lithium, this band which is formed, if I can make another diagram which is equivalent to this diagram, I have a band here which is a 1s band, and I have a band here which is a 2s band. Now is the 1s band completely filled? Yes, because the 1s orbitals were completely filled. So this band is completely filled. But is the 2s band completely filled? No, it's only filled up to half the bandwidth. So it is filled only up to here. And there is a natural gap between the 1s band and the 2s band because when the atom started off, there was a gap between the two levels. And the fanning is not large enough to overcome the entire gap. So this gap persists when bands are formed. This is the energy gap. And since the 2s band is partially filled, what is lithium? Is it a conductor or an insulator? It's a conductor. So this is the origin of gaps. I will continue with this discussion on Friday. Tomorrow there is going to be a tutorial or a recitation session in which we will do some problem solving.
Tomorrow?
Yes, tomorrow there's a special. I don't know if Mudassir has announced it, but there is going to be a session tomorrow. You're free at that time. I don't remember the time. We'll email you. Mudassir will email you. Now I can answer individual questions after.